So this is a really powerful analysis. And we've got to be careful because not all ODEs have equilibrium points. I just want to emphasize here that an equilibrium point is a value of y. It's not a value of t. It's a value of the dependent variable such that dy dt is 0. Since t often represents time, time changes with or without us, and therefore values of t can only cause brief moments of zero slope. An equilibrium point, however, is a value of the dependent variable for which dy dt equals 0 for all time. So let's take a look at one example where that is the case. Consider dy dt equals the product of y minus 1 and t minus 1 and find the equilibrium points, and explain why it is not possible to describe the sign of dy dt for all y above and below the equilibrium point. So what I'm going to do here is I'm just going to draw my y-axis vertically, so same number line as we had up here. I see here that if I set this equal to 0, 0 equals y minus 1 times t minus 1, the only value of y that will make this 0. Now clearly if t is 1, then this whole right-hand side becomes a product involving a 0 factor, but the only value of y that will make this 0 is if this factor here is 0, and that means y is equal to 1. So that's our only equilibrium point, when y is equal to 1. Okay, but what happens if y is bigger than 1? Well, if y is bigger than 1, let's say at y equals 2, then that means dy dt is going to equal 2 minus 1, which is 1, times t minus 1. Okay, so just knowing that y is 2 does not allow me to conclude that dy dt is positive or negative, because look at this. Dy dt can still have an issue in that if t is bigger than 1, then dy dt is going to be positive, right? So if I put in time 2, 1 times 2 minus 1 is positive 1, and therefore I'm going to have a positive slope. But if t is less than 1, so for all moments before time 1, even though my value of y is 2, which is bigger than my equilibrium point, in this case, dy dt is less than 0. So the key here is that it depends on y and t. And so just knowing what the equilibrium point is, even though it is the case that y equals 1 is an equilibrium point, what happens when y is bigger than 1 or less than 1 begins to now also involve t. Okay, so anytime this first factor is not 0, like it is when y is 1, then we now have to take into account the extra analysis of looking at t. So usually we don't want to do this sort of equilibrium analysis when the function does involve t, because realistically that value is going to affect the rate of change as well. So another important fact to notice is that when dy dt is only a function of y, that is, the model is called autonomous. Remember, that just means that the rate of y depends only on y, like automatic, autonomous, autoimmune, etc., and does not directly depend on t. Then for all y between any two equilibrium points, dy dt maintains a constant sign, either positive or negative. So what I'm referring to here is back in problems 1 and 2, all we needed to know was the value of y, and that told us everything that we needed to know in order to say dy dt is positive or negative. Why? Well, because the right-hand side did not involve time. Same thing here. The right-hand side did not involve time. In problem 3, which was not an autonomous equation, this one depended on both t and y, we could not conduct this analysis. So we could not conclude that dy dt is always positive for y bigger than 1. Since the value of t is not important in determining the slope, a t-axis is not necessary in understanding long-run behavior, and so we draw a single y-axis, as we've been doing, with the equilibrium points and arrows along the intervals showing the behavior of y. So I'm basically now, instead of drawing this horizontally, what we've done here is we've drawn a phase line, and a phase line just tells you where the equilibrium points are and what the sign of dy dt is by using arrows within the different phases of those intervals. Or you could say phases or intervals. Okay, so here let's go ahead and conduct 4 different analyses. We'll do one for dy dt equals y minus 1. So for dy dt equals y minus 1, we set that equal to 0, and we get y equals 1. So that means that if I draw an equilibrium or a phase line, I label the equilibrium point y equals 1. And now I just have to figure out what happens when y is bigger than 1 and when y is smaller than 1. So notice no t. These are all autonomous equations. So when y is bigger than 1, that means this is going to be a number bigger than 1 minus 1, which will be positive. So that means that the value of dy dt is positive, which tells us that y is increasing. Now, when y is less than 1, clearly you're going to take a number smaller than 1, subtract 1 from it. That will make it negative, which means that if dy dt is negative, y is decreasing. So we call this, we actually start to classify these equilibrium points as well, and we call this equilibrium point here a source. And the reason we call it a source is because things source away from it. In other words, if you're slightly above or below that equilibrium point, it's very unstable. All the solutions are going to move away. So we often call this an unstable equilibrium point. And we want to know that because this might have implications in different disciplines. If you're not at the equilibrium point, you're slightly nearby it, everything will move away from it. In the second example, we have the same equilibrium point, but now we're going to have different things happening for when y is bigger than 1 or when y is less than 1. So in this case, if y is bigger than 1, 1 minus a number bigger than 1 is going to be negative. Therefore, y is decreasing from up here. I want to label everything here also to be clear. And then when y is less than 1, 1 minus a number smaller than 1 will be positive. And so y will be increasing up towards the equilibrium point. So basically this means that from both directions, if we're near the equilibrium point y equals 1, we're ultimately going to approach it. And much like the water in your faucet goes to the drain in the sink, we usually call this a sink. It sinks all the solutions for initial conditions surrounding y equals 1 will sink into it. This is often called a bistable. It's stable from both directions. In number 3, we have 1 minus y squared. Not surprisingly, we're going to get exactly the same equilibrium point, y equals 1. But in this case, y equals 1, well, it doesn't matter what the sign of what's inside of here is. If you square it, it's going to be positive. So that means we're going to have y is increasing for values above 1, y is increasing for y values below 1. And so since we're stable from one direction, if y starts out less than 1, then y is going to approach 1. But if y starts off bigger than 1, it's going to move away from 1. So we often call this a type of equilibrium point a node. This is called a node, and it's called monostable. And you can imagine why. Mono means 1, so it's stable from only one direction, but unstable from the other. And finally here for the last problem, for dy dt equals y minus 1 squared. Sorry, I wanted to put negative y minus 1 squared here. That same equilibrium point is the one that we'll get, except that now you can verify that the slopes surrounding y equals 1 will both be negative. So if y starts off bigger than 1, it will decrease towards the equilibrium point of 1, and then it's stuck in equilibrium. And if y starts off less than 1, it's also going to decrease, in this case, down towards negative infinity. And this also is called a node, and this also is called monostable. So you have two types of nodes. Nodes just mean that on both sides of the equilibrium, the arrows point in the same direction. So again, this just tells us what's happening to y over time. We don't actually have time in these equations. We don't know how long it's going to take. For example, in example 4 here, we don't know how long it's going to take if y starts off as a half, how long it's going to take to get to negative 500. This is purely a qualitative analysis. Now, we just described classifying an equilibrium point, and we could classify them as a sink. Depending on what discipline you're in, sometimes people use the word attractor, right? Because this is sort of attracting, it's like sucking all the solutions into it. or bistable. If both arrows point away from the equilibrium point, we say that the equilibrium point is a source, and that was this situation here. Or repeller, you could sort of think about it as magnets with like poles. They're going to repel each other. If one arrow points toward and the other points away from said equilibrium point, then we call it a node or monostable. And there are two examples of nodes. Those are these two. Okay, now you can have more than one equilibrium point. In these models, when we solve dy dt equals 0, we only came up with one, namely because our functions have been linear so far. So let's just go ahead and complete this analysis. We sort of already did this for the loan model. We found that the equilibrium point is y equals 10,000. Now all we'll do is we'll just look at this as the y-axis. We said y equals 10,000 is that equilibrium point. If your balance started higher than 10,000, then your balance would basically continue to increase because you're not paying enough to even take care of the interest charge. But if you take out a loan less than $10,000, it will decay and eventually you'll pay it off. It'll become 0. Now, one thing I want to point out as well is that we haven't plotted the t-axis, right? Let's just pretend that this is the t-axis here. What I would actually be able to draw is just based on this behavior. I don't know the exact shape of the curves, but typically if y equals 10,000 is an equilibrium point, meaning that if you ever have a balance of $10,000 and you make a $100 payment, you're charged 1% per month, your balance is always going to remain at 10,000 for all time. So for this initial condition, y equals 10,000, your balance will forever be 10,000. If it starts off slightly higher, then it's actually going to progressively become more exponential because of the fact that when you're taking 1% of growing values, that amount actually gets bigger as well. And if you start off with a balance of less than 10,000, at first it kind of takes a while to really knock some of that balance off, but eventually you'll start to get exponential decay, and that balance will eventually approach 0. So notice that we could kind of superimpose this t-axis, but it's not necessary because this one phase line tells you everything that you need in terms of long-run behavior of those functions. Now, if you wanted this exact curve, you just have to solve this model and solve it using separation of variables. So it depends on what our task is, which will ultimately determine what type of tool we use. Let's do one more, dy dt equals sine of y. So if we set that equal to 0 to find equilibrium points, well, wait a minute, sine of y we know oscillates, and basically sine of y is 0 for y equals 0. And let's see, sine, if I look at the sine function, sine of t starts off at 0, comes to 1, back down to 0, down to -1, back up to 0. And this is at pi and 2 pi. So same thing over here. And that's going to be at negative pi and negative 2 pi. And then at every increment of pi, it again reaches 0. So 0, we'd have plus or minus pi, plus or minus 2 pi, etc. And sometimes you'll see people write it like this. They'll say y equals something like n times plus or minus n pi. Or you don't even need to use plus or minus. You could just say something like k times pi, where k is any integer. So that's plus or minus 1, plus or minus 2, 0, plus or minus 3, plus or minus 4, etc. But how do you draw a phase line for this? Well, unfortunately, since this thing goes on forever, you can kind of do this ... on either side and plot a few of those equilibrium points just to show the pattern. Y equals 0, y equals pi, y equals 2 pi, and then here y equals negative pi, y equals negative 2 pi. Now the question is, what is happening on these different intervals? So we have lots of intervals. We'd obviously need to plug in a value between, say, 0 and pi into the sine function and see whether the sign of it is positive or negative. But I want to propose another idea. Instead of having to plug numbers in, if I look at this graph here, and this is the dy dt axis, plot it against y. Now this is a weird graph to look at because your output is actually a slope. Your input is actually a value of the dependent variable. Therefore, if I wanted to plot this function, I'd have to plot dy dt, my vertical, against y, my horizontal. And what that allows me to do is to say anywhere the portion of the graph is above the horizontal axis, those are all positive values of dy dt. So between 0 and pi, dy dt is positive. So between 0 and pi, I'm going to draw an arrow that points up because y is increasing if dy dt is positive. Now from pi to 2 pi, I see that the dy dt graph is below the horizontal axis, which means dy dt is negative, and that means dy dt is decreasing. Wrong interval. Sorry about that. We actually want that here. There we go. And again, from 2 pi to 3 pi, we see that that portion of the graph is above the horizontal axis. So above here, I could draw an arrow pointing upwards. You probably get the pattern. So back here between 0 and negative pi, the portion of the graph is in the negative dy dt region, in the negative portion here. So it would look like this. And then here, its graph indicates that dy dt is positive. So really, these are just alternating. And if you look at these equilibrium points to classify them, this one is a source, this one is a sink, and then a source, and then a sink. And it looks like they're going to be alternating in characteristics. So that's one with infinitely many equilibrium points, and that's perfectly fine. Usually we just indicate it by saying something like, well, there are infinitely many of them. Here's a sample phase line. Good news in a lot of applications is that you're not gonna let y be 3000 pi, for instance, because likely the domain of your model will tell you, you can't have y values that big, or you can't have negative y's. So this is a mathematical phase line. We have also practical phase lines that only look at equilibrium points that we know are meaningful and part of the reality. So again, if y was a population size, then having negative y's just wouldn't make sense. So again, we do not typically draw phase lines for models that are not autonomous. So if dy dt depends on both t and y, or it only depends on t, we don't draw these. And the reason is going back to this example where if t is involved, then the value of t also has a say in whether dy dt is positive or negative. And so the value of y alone does not allow us to accurately draw a phase line. So at that point, you could try to do it for different values of t, just draw multiple phase lines, but that does not benefit us. It does not add value to our analysis.